Okay, so this is lecture 2, part 2, and what I'd like to do now, last week we did that birthday problem, which was a good warm up, good big picture type problem. We're going to do another one right now, and there's a few mentions of this in the textbook, but this is also a good segue into summary 1, and it's a lot of the numbers we're going to cover right now I covered in my 2008 paper, so we'll just kind of warm up on a few numbers. So what I'm going to ask you to do for me right now is tell me how much energy it takes to run a human being for one day. How much energy is it? So I've got 3 students in the classroom right now, and we'll just kind of take a cold poll. And so what do you think, Todd? What's an energy per person per day?
2,000 calories.
Okay, I've got 2,000 calories, and what I'm going to do here, I'm going to put 2,000 in the upper left corner of the matrix, and I'm going to label it as CAL, so kilocalories. Rain, what do you say?
A pound and a half T-bone steak.
Pound and a half T-bone steak. We could do this. We could put mass.
Imagine it's probably about 800 calories.
Yeah.
600 to 800.
LB. So 1.5.
Yes.
1.5 pounds. Tynan, what do you think?
On average, about 1,800, 2,500 calories.
1,800, 2,500. Okay. So I'll just throw 2,500 down there.
150.
One thing that comes out of this right away is that we've got different units for energy, and of course that steak is energy. It's food. But the point is, we're going to have to do some conversions here. So what the conversion I'd like to do, I'd like to put this in first in joules and then in megajoules. And Tim Chester had a neat little converter on his smartphone, his calculator. In the back of your Everett text, there's also some conversion tables. But really, all I want to do here is go from calories to joules. So if you've got a way to do that with either your calculator, textbook, online, go for it. I'm just going to use the internet. I know Google has a converter built right into it. So let's just take those numbers and convert them. A 1.5 pound. Does that include the bone too? I mean, that's a pretty beefy chunk of meat, man.
You had $6.99 a pound at Rose Hours, so I stocked up. I've been eating real good lately.
Nice.
Yeah, that includes the bone. Bone's
Okay.
probably a solid half pound, so I think you're probably only really getting 16 ounces of meat.
Okay.
Actually, 13 ounces of meat, because there's definitely some fat on there.
8 million joules for 2,000 calories.
You get 8 million? Okay.
1 calorie is approximately 4,000 joules.
Yep. Yep. And so we'll go with that. What are you getting for megajoules? How are we going to go from joules to megajoules?
Did you say 1 calorie is roughly equal to 4,000?
8 megajoules? Yeah, 1 calorie is approximately 4,000 joules.
I'll do it up here.
2,000 calories is 8.3736 megajoules.
That sounds about right. Okay, so here's a little online converter. I'll type in the 2,000, click on convert, and there we go. Yeah, just north of, so 8.3, 8.4 megajoules. I'll go ahead and type in 2,500, see what we come up with there. So 10. 10 million joules. And you can see I've left off the significant digits, but that's okay for our purposes at the moment. I'm just using 1 sig dig. So this is the number that I was after here. 10 megajoules to run a human person. Now, another concept I want to get out right away is that we need to make the distinction between energy and power. So anybody know off the top of their head what the relationship is between energy and power? How do you get from one to the other? What do you do?
Joules over seconds? Or energy over time?
Yeah, there we go. So power equals energy over time. And I think where you were going with that, and so to take this from just sort of from words or names into units, what we're going to do, that's going to be watts. So 1 watt equals 1 joule per second. Okay, and so you can see we've got our human metabolism in joules. We should be able to now figure out how many watts it takes to run a person. So let's figure out what our wattage is, and do it for 8, do it for 10, because not everybody's running the same speed. But so take a second and tell me how many watts.
It'd be 10 million watts, wouldn't it? If one.
So here's the just a good warm-up problem, something to think about. We're going to visit it more over the course of the semester, but here's how I solve the problem. So I know from what I just told you a second ago that the definition of power is energy per unit time. And in a sense, we don't really know what energy is. I mean, you were all able to tell me that you're going to eat 2,000 to 2,500 calories of energy per day, and we kind of reasonable estimate from that. And in a sense, we don't really know what power is, and for that matter, I'm not sure anybody really knows what time is either. But we've got all three of them right here in one equation. We got power, energy, and time all in one equation. And as you were saying a second ago, we can just take this little power equation and just treat it like an algebraic expression and just say that the definition of a joule equals a watt second. So, I just manipulated that algebraically, and someone says, what's a joule? Well, it's a watt second. Well, what's a watt? It's a joule per second. Well, what's a second? You can kind of just keep going around and around with it like that. But that is the formal physical definition of the relationship between energy, power, and time. Now, to then solve this problem of what is one human power, we will, let me start right here. And obviously we have one equation, right? And if you have one equation, and we have three variables. So in order to solve the problem, we have to know two out of those three variables. Well, and which two do we know? We know time and energy. Yeah, we know how much energy a person eats in a day, and we know how much time there is in a day. So we know this one, and we know this one. We got one equation, one unknown. We should be able to solve that guy. And typically, we keep the thing we don't know on the left side. That's where it is already, so we really don't have to do a whole lot of manipulation. We'll be out of here in 7 minutes.
I didn't know you guys had class.
It's top secret. So on the top, we just plug in the value of the joules, and there are obviously two important components. One's the value, 10,460,000, and the other is the units. Do not forget the units. We did a little bit of that last or on Tuesday, and that's as critical as anything. That's your X's and your Y's that you're dealing with in your algebraic expressions. Now, we need to figure out how many seconds there are in a day, because a watt is a joule per second. And it's easier for most people to just, break this out into little chunks. I heard a couple of you say, well, I know that there are 60 seconds per minute. Well, I don't want to know I don't have the amount of energy per minute. I've got the energy per day. So I got to get out to that day column. Well, I know there's 60 minutes in an hour. Well, I don't know how much energy I use in an hour. I got to get all the way out here. 24 hours per day. Now, when I go through, start canceling units. Minutes cancel with minutes. Hours cancel with hours. The day is still there. The seconds are still there.
So we multiply those three together, so we get how many seconds we have in a day.
Yeah, another way to do it. I think what I did on this guy. If you start off with your 10,460,000, and then you can start dividing. Divided by 60. Divided by 60, divided by 24, equals 121.
Now, where did you get the number 10,460,000?
That was the conversion of 25.
Yeah, we got
2,500.
2,500 calories is that many joules.
Okay.
10,460,000 joules. So what we're left with, well, let's do it one more. Let's be a little more. This is actually that many joules per day, if you remember, just to be a little more complete. So I'm like, what do I do with that day? Well, I can get rid of it because we knew that the person consumed the 10 million joules per day. So now the 2 day units are gone, and now we're end up with 121 joules per second. And you know what? I think I want to rewrite this so I'm not getting you guys too confused. A better way to write that would be P. A better way to write that is P equals energy over time. And so this guy right here is how it's written in its dimensions. And here how it's written in units. And we'll spend a whole lecture distinguishing between units and dimensions. I mean, we've already done it once today. We've said that calories are the units of energy. Okay, so so that is one human power right there. And as we get through the semester, I think what we'll get to when we get to my summary paper, and we'll do that in the last half hour here when we move over to Grizz House 9, we'll look at technological power. And we'll find that it's substantially more than human power. Does that sound high to you guys? Low?
121 watts. I would have thought it would take more.
I know. It's remarkably low. I mean, it's amazing how efficient we are with our energy. I mean,
that's assuming you actually eat 2,500 calories.
Well, everyone's burning at a different rate, but I mean, your brain's responsible for burning a lot of that. So.
I know me personally, I might get 2,500 calories every 2 days.
Yeah. Well, if you don't, regardless of what you eat, your body's still going to consume energy. It's going to start consuming itself. So, yeah. Okay. Well, we'll wrap it up there, and then let's head over to Grizz House 9.